Have you ever wondered why chlorine and fluorine react in almost the same way, or why sodium and potassium behave so similarly with water? Well, it's no coincidence, it's all about their group in the periodic table. In chemistry, groups are the vertical columns. There are 18 of them, and each one represents a family of elements with similar outer electron arrangements. The group number often tells us the number of valence electrons, the electrons in the outermost shell responsible for chemical reactions. For instance, sodium, with an electronic configuration of 2,8,1, is in group 1 because it has one valence electron. So, when you look at a group in the periodic table, you're not just seeing a column, you're seeing a chemical family united by electrons. Now, let's take a walk down the groups and classify the element types we find. Group 1 contains the alkali metals, light metals like lithium, sodium, and potassium, each with one valence electron. These are the metals that fist, pop, and explode in water. Group 2 includes the alkaline earth metals like magnesium and calcium, still reactive but a bit more reserved than their Group 1 cousins. From groups 3 to 12, we meet the transition elements like iron, copper, and zinc, known for their shiny surfaces and colorful compounds. Then come groups 13 to 16, the post-transition elements, they're the bridge between metals and nonmetals, featuring diverse behavior. Finally, group 17 brings us the halogens, aggressive nonmetals like fluorine and chlorine, while group 18 houses the noble gases, stable, inert, and dignified elements like neon and argon. Every group has its own signature behavior thanks to those valence electrons. Let's talk about the middle block, the transition elements, and those mysterious elements tucked below the table. Transition elements, found in groups 3 to 12, are all metals with partially filled d orbitals. Take scandium, for example, atomic number 21, electronic configuration 2,8,9 with a d orbital starting to fill. These metals are known for forming colored compounds showing variable valency acting as industrial catalysts, but the story doesn't end there. Below the table are the inner transition elements, the lanthanides and actinides. Lanthanides, from cerium to lutetium, are shiny, rare earth metals. Actinides, from thorium to lawrencium, include some of the most radioactive elements like uranium and plutonium. Lanthanides belong to period 6 and actinides to period 7. Both series make up the F block of the periodic table. Let's observe what happens when we move down a group. The most important rule: the number of valence electrons stays the same, but the number of shells increases. This causes the atomic size to increase and the metallic character to go up because the outer electrons are now farther from the nucleus and easier to lose. So, electronegativity decreases and reactivity patterns shift. For instance, in group 1, lithium is mildly reactive, but potassium and francium explosively so. Now let's dive into the alkali metals, the bold, reactive stars of group 1. Each has one valence electron, making them univalent and highly eager to lose that electron to achieve noble gas stability. They are soft, light metals, highly reactive, especially with water, good conductors of heat and electricity, strong reducing agents because they easily donate electrons. Let's take an example. When sodium reacts with water, it forms sodium hydroxide and releases hydrogen gas. Chemical equation: to now solid plus to H2O liquid gives to now H aqueous plus H2 gas. Imagine a family of elements that are super reactive and always just one electron away from perfection. That's the halogens. They have 7 valence electrons, making them univalent nonmetals with a strong desire to complete their octet. Their electronegativity is sky high, starting with fluorine, the most electronegative element of all, and gently decreasing as we move down to iodine. These elements are powerful oxidizing agents ready to snatch up an extra electron in no time. And they come in all forms: gases like fluorine and chlorine, a liquid like bromine, and a shimmering solid like iodine. Truly, the halogens are a diverse and electrifying group in the periodic table. Let's quickly recap what we've uncovered about groups in the periodic table. Each group forms a vertical column of elements that share the same number of valence electrons and hence similar chemical properties. As we move down a group, the valence remains constant, the atomic size increases, the metallic character increases, the electronegativity decreases. We looked at Group 1, the alkali metals, reactive, metallic, and electropositive Group 17, the halogens, electronegative, oxidizing, and nonmetallic, and the transition and inner transition elements which bring color, complexity, and catalytic power to the periodic table. From fireworks to disinfectants, batteries to nuclear power, the groups of the periodic table explain it all. I hope this session helped you see how group trends reveal the hidden logic of chemical behavior. In the next topic, we'll zoom in on periodic properties like atomic radius, ionization energy, and electronegativity. Until then, stay curious and keep exploring the patterns of the periodic world.